Okay, the flow of heat is from higher temperature to lower temperature. Okay, so what that mean? If you have a object and if you have a small object, so we have two different objects. This object has 25 Celsius. This temperature of this object is 25 Celsius. But this object has a 100 Celsius. If those two objects merged together, what happened? So if those two objects meet them together, where the flow, the heat will go, moving, okay? The moving from higher temperature to the lower temperature, which means the heat will be transferred from this small object to the higher object, to the big object, okay? So the heat transfer is not based on the size of the object. It's based on the temperature, okay? It's based on the temperature, okay? The higher temperature, then they're always moving from higher temperature to the lower temperature, okay? It really doesn't matter the size. Okay? It really doesn't matter the size. So this is the heat transfer, okay? So now, if we talk about this moving from higher to lower, then the heat going to have two directions. One, if we're absorbing heat, so now the next one, we're going to talk about two different processes. One process is called exothermic. The other one is called endothermic. Okay. So now the exothermic and endothermic is talking about this is all talk about the system, okay? The exothermic and endothermic. You can write as a process or as a reactions. Some of reactions is exothermic, some of the process is exothermic. Endothermic can also write all process or reactions. Okay, but exo, endo, that means exo, that means the releasing system is releasing heat. System is releasing heat. Okay, the heat is go out. Okay, is go out. The releasing you can also write as a producing. Okay, producing or leaving. Well, but endothermic, this means the system is gaining heat or absorbing heat. Okay, so now based on this, you will see the direction. Okay, you will see the direction, which means an exothermic, that means this, we have object, and if we talk about we're observing this object, so the object is system, right? And this system is releasing heat, which means the heat is transferred from this object. It go out, okay? This object is go out, the releasing heat. And then this is called exothermic. But if you have objects and they are going to absorbing the heat, so they're gaining the heat coming out, coming into this project, and then this one is called endothermic. So my question is, okay, one is gaining, one is losing. Do you think how the temperature change? Because we talk about the heat is is changing the temperature, is used to change the temperature. So what do you think? Exothermic and endothermic. To the object itself, which one is raising the temperature? Which one is decreasing the temperature?
Exothermic is decreasing the temperature.
Yes, exothermic is decreasing the temperature of the object. Okay, is decreasing the temperature of this object. Okay, the endothermic is increase the temperature of this object. Okay, so for example, we're burning the wood, right? So old time, the people burning the wood in the fireplace. Okay, so you feel warm. You feel warm. What do you think? You're burning the wood. Is this exothermic or endothermic? For the wood, that's exothermic. That's great, okay? Because the exothermic and endothermic is going to be compared to the system, okay? Yeah. If you're talking about your body, then that's an endothermic thermic process, because your body is absorbing the heat. So that's why your body, you feel warming, and then the temperature of your body is getting higher. But for the wood itself, they're releasing the heat, right? So the wood itself is releasing the heat. So for the wood is exothermic. That's great. Did you get it? Okay, yeah. So we have the different object. You need to think about what kind of system it is. Okay, yeah. If you're talking about the wood itself, that's exothermic. Yeah. If you're talking about your body, then that's endothermic. Is that right? Okay, yeah. So again, but this also always is changing the temperature. Okay, so this is compared the system. And another thing is, okay, once you open your refrigerator and you feel cold, okay, so think about how the heat flow goes. Once you open the refrigerator, you feel cold. How the flow of the heat go?
The hot air outside the refrigerator is going in.
Yes. Okay. And yes. So we talk about the heat flow is always from higher temperature to the lower temperature. You feel cold, it doesn't mean the cold area is going to you. Actually, it's because the refrigerator is sucking the energy from you. So that's why you feel cold. Your body is an exothermic process. You're generating the heat out. But the refrigerator, since they have a lower temperature, they're absorbing the heat, continuously absorbing the heat from you. So that's why you feel cold. It's because of that. Okay? Yeah. So think about the heat flow always from higher temperature to the lower temperature. Okay? They always go from high to low. This is the flow. Okay? So the lower temperature one always absorbing the heat. The higher temperature one always producing heat or releasing heat. Okay, yeah, that's a exo and endo, the difference between exothermic and endothermic. Are you clear? Okay. All right, so now we're going to talk about the sign. Okay, we're going to talk about the sign. So since the exothermic is talking about exothermic is releasing heat, but this one is talking about is a system releasing the heat. Okay, we're already right over here. The system is releasing heat. So if you're right, that's gonna be the heat. Okay, the heat of the system is going down. Okay, the heat of the system is going down. but the heat of the surrounding will going up, right? We talk about the system and surrounding, those two are coupled. If the system losing the heat and the surrounding have to absorbing the heat, because the energy is never be destroyed or generated, okay? They have to, one is transfer the energy out, the other one have to absorbing the energy, okay? Yeah, so this is exothermic. But endothermic, then that means the system is gaining the heat and the surrounding will losing the heat, okay? So the system gain the heat, the surrounding must lose the heat, okay? The surrounding must lose the heat, okay? So that is the difference, that is difference. Or if we write the sign, those heat can has a sign. And then we're going to talk about the heat will be a negative sign. And this heat will be a positive sign, okay? So what that mean? That means the heat for the exothermic, the heat is a negative sign. For the endothermic, the heat is a positive sign. The negative sign, the people then think about how come they're producing heat? Why this is a negative sign? When you think about the system. So this first, the system, think about your firewood. Wood itself is losing the heat. After the burning the wood, what's left? Is there any wood? Probably not, right? You only have an ash left over. So all the energy of the wood is burning out, it's giving away, okay? Yeah, so that's why the system itself, the heat is decreasing all the time. So that's why we're using negative sign to represent, because the system is losing the heat, okay? So losing, that means negative. But the Q larger than 0 for endothermic, because the system gaining the heat. So gaining, that means positive. So we have a positive sign for endothermic. All right, so let's take a break. Okay, after the spring break, you're probably not used to wake up too early. Okay, right? Yeah. So today I'm going to talk a little bit slow, but the next class I'm going to go quick. Okay, yeah. So endothermic, exothermic. Okay, yeah. Here we that some of the reason when we talk about endothermic or exothermic reactions, okay, now we talk about process or reaction. The reason we're talking about process and or reaction, that's because some of the physical change, like from phase to phase, from gas to the liquid, or from liquid to the gas, there also has a heat change of there, but those are not the chemical reactions. Okay, yeah. So we're calling those are process. Some of the chemical reactions, they also has endothermic or exothermic. Okay, so that's why here we're going to talk about the difference. First, we talk about the process. Why process can also has a physical change. Okay, and then first we need to talk about the phase change a little bit. Solid, liquid, and gas. Okay, so now we only talk about those three different change, the three different phase of there. So what do you think? Which temperature for the phase? Solid, liquid, and gas, which temperature is higher? Suppose.
Yes.
Gas suppose has a higher temperature, right? You can think about the, what's that? You can think about the water, right? The boiling water, the vapor should be higher than 100 Celsius. Okay. Liquid between 0 from 100, and ice is below 0, right? So obviously gas has a higher temperature. So if if we melting the gas, melting the water, what do you think? Is it endothermic or exothermic? Well, melting. Melting is from which phase to which phase? Okay, melting, that's from solid to the liquid. What do you think? Is it temperature increase or temperature decrease? Temperature increase. So that's going to be endothermic, because the system is going to, the water need to be heat up, right? If the water is not going to heat up, how come they're going to melt? No, right? So you're from solid to the liquid. This is the endothermic. So that's why I want you to think about temperature. Okay, if you know the temperature change, then you will see whether it's endothermic or endothermic, right? Because you have to absorbing the heat to get the next level of the space, right? You're from lower temperature, which is solid, to the higher temperature liquid. You have to, the object have to absorbing the heat. Then that must be an endothermic process. That makes sense, right? Then if you go opposite way, how about freezing? Freezing, then that's going to be exothermic. Okay, if the from solid to liquid is endo, then the opposite way, liquid to the solid, have to be exothermic. Okay, so liquid has a higher temperature than the solid. So if the liquid go back to the solid, they have to release the heat out. Otherwise, they're not going to freeze. Okay, otherwise they're not going to freeze. That makes sense, right? Okay, so exothermic, endothermic. So when the phase change, we have six different phase change. Melting, freezing, solid to liquid, liquid to solid. And then let's just be clear about this. I'm going to moving this down. then you will see from solid to the liquid, from liquid to the gas is doing the same thing. If you have a liquid to the gas, from low temperature to the high temperature is still endothermic because the system needs to absorbing the heat, which means the boiling. The boiling is also this, okay? We can also call this phase change not just called boiling, it's called the evaporation or a vaporization. Vaporization means from liquid to the gas, okay? And then there's another phase change, which is directly from solid to the gas, okay? Directly from solid to the gas, this is what we call the sublimation. Sublimation, this is from solid to the gas. And this is obviously also endothermic. So you will see from lower temperature to the higher temperature, they always is endothermic. Yes.
Why are plasma?
Plasma, this is state. They all, yeah, plasma is also a state, but the plasma is even stronger than has an even higher temperature than the gas. In the plasma state, those gases molecules is not a molecule itself. It's already ironized. It's become ions. So normally the behavior of those is quite different from gas, liquid, and solid. So that's why in Chem 1, we're not talking about this topic. It doesn't mean this one is not here, okay? Yeah, plasma is also one kind of the state, but in Chem 1, we're not talking about plasma, okay? Yeah. So the solid, liquid, gas, those three will the endothermic. From lower temperature to the higher temperature always is endothermic, okay? And then you go opposite way from higher temperature to the lower temperature, they must be exothermic, which means they're releasing the heat out, okay? So the freezing from liquid to solid. And you will see from gas to the liquid also. If you're from gas to the liquid, this phase change, the name is called, what is this called? From gas to the liquid.
Condensation.
Condensation, okay. Condensation from gas to liquid, and this is an exothermic process. It produces the heat, okay? The last one is called deposition. Deposition, that means directly from gas to the solid, okay? From gas to the solid, that means a deposition. And this is also an exothermic process, okay? Sublimation, some of the example like dry ice. You have a dry ice, direct go to the CO2 gas, right? There and they have a smoke out. So that is the sublimation. The deposition go opposite way. The CO2 directly become a dry ice. Okay, so those phase change or the process, 3 of them is endothermic, 3 of them is exothermic. Are you clear? Okay, yeah. So but obviously when we talk about this, we're not going to sometimes I'm going to trick you. For example, what do you think? If I'm saying cooking an egg, for the egg, what kind of process it is? I'm cooking egg. That's going to be an endothermic because we're heating up the egg, right? So when you cook something, the something must be an endothermic process, okay? because you're heating up those stuff unless you're making salad. Okay, so then you don't have to. Okay, but the cooking eggs and the egg is an endothermic process. Okay, or if you're baking bread, and the bread is also endothermic. Okay, yeah. For the, I think this is pretty much, I'm going to talk about the process. And then if you're talking about the chemistry reactions, the reaction is going to be very obviously. For exothermic reaction is very, very opposite. Exothermic reaction is very obvious. Any of the combustion reaction, those are all exothermic reactions. They are going to release the light and also release the heat. Okay, so and this is also a very big signature for the combustion reaction. They are releasing the heat and also releasing the light. So if you see the firework, all the firework, those are exothermic reactions. Okay, they're releasing the heat and also the light. If you're burning the Bunsen burner, okay, those are also exothermic reactions. You feel warm, okay, but itself we're consume those objects, okay. But for endothermic, this reaction is pretty minor. You're not going to see this very obviously, okay, because they're going to absorbing the heat from the surroundings. So I'm going to show you one of the video. This is a pretty interesting video, and we will see how the endothermic process going.
Barium hydroxide, and I've got some ammonium chloride. And what I'm going to do is mix this together, and hopefully we should see a endothermic reaction. Yes. What hand stuff? Oh, it just lives on my desk. I was dropping off the pot, so yeah, I need to be not covered in blood. So what I'm going to do to show how exothermic is, how cheap this is taken in, I'm going to make this wooden block and flip it. Okay. Now, you will see right number 7. So I'm going to mix these two things together and carefully. I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now we want to see endothermic, so it's going to be a little bit more subtle. So I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to drink it. Okay, if you put that in coffee, oh, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the best thing you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom. And that is pretty cool. Well, I haven't got. In fact, I have got a thermometer. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? 0. So
Freezes at 10.
this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going.
Will it freeze our fingers?
If you had it on there, yeah, it would start to. In fact, there's actually ice crystals forming on the side of there.
Can I touch the side? It's
cool.
so cool.
Okay, so that means it's endothermic process. Okay, so that's the endothermic. What happened here is you're having a beaker, right? And then we'll have a block over here, and we're putting some more water. So the water is on. We're putting the water, and the reaction is going on in the beaker, and then this is an endothermic reactions. This is endothermic reaction. So during the process of this reaction, the reaction need to keep continuing absorbing the heat from the surrounding. So they're going to decrease the temperature. We're talking about surrounding. That's including everything except the reaction itself. Okay, it's going to be increasing the beaker, increasing the water, increase the block, even increase, including the air in the surround. Okay, so they're going to absorbing the energy from everything around it. So the water is going to losing the heat, then the temperature of the water is going down, and then they're going to freeze. Okay, yeah, and then if you see the air, also the water in the air also going to freeze in the outside of the beaker. Okay, yeah, so this is what happened for the reaction. This reaction, anyway, endothermic, it's not that easy to see. Okay, yeah, so this is endothermic reaction. That's cool, right? Yeah, I think that is pretty cool. All right, so this is what we're talking about here. And then the next part, we're going to talk about the unit of the heat. Okay, the unit of the heat. One more time, endothermic. That means Q is going to be a negative sign. At endothermic as Q is a positive sign. The next one is talking about the heat, the unit of heat. So the SI unit, which is the international system, the unit we're using joule as the heat. Okay, the joule as a heat. So if you write the symbol, it's just a capital J. But this unit is really, really small unit. So most of the cases we're not in chemistry, we're not using joule. Okay. Sometimes we probably using kilojoule. That's probably okay. We're using kilojoule. So which means the 1,000 joule. Okay. We're not using joule, instead of we're using kilojoule in this some of the case. And there are some other units. It's called a calorie. Using the calorie. So the calorie, this is one of the units. Another unit is called the food calorie. Okay, so the calorie and food calorie definitely is different. Okay, so the food calorie we also call is a kcal. Okay, and then you will see the difference. So the calorie is just calorie, and the kcal, that means 1,000 calorie. Okay, the food calorie is the calorie that you can see in the back of your the food. So if you buy any food, you get a donut. It says 300 kilojoule. Okay, 300 calorie for a donut. It's pretty big, okay? It's already big enough. Okay, that calorie is not this calorie, okay? 300 calorie that you see in the back is the food calorie we're talking about. It's a 300 kilocalorie. It's pretty high, okay? And in our body, we probably just need how many for daily usage? 2,000. That's for the small size person, okay? 3,000. That's for the bigger size. If you're living in the Wisconsin or even north, okay, you probably need 4,000. Okay, yeah. Last time I saw some people on YouTube. They're compared the army ration for different countries. Okay, they realize the Russian people, their ration has about like 4,000 the calorie for daily usage. Most of those are fat. It's just a fat. Okay, yeah. To if they are stand outside, that's gonna be really cool. So that's a food calorie we're talking about. I just give you those two, but we're not using this in our class. Just recognize we do have a calorie and a food calorie, but usually the food calorie we call the kcal. Okay, yeah, and this calorie is much smaller. It's 1,000 times smaller than the food calorie. But most of cases we're still using joule and kilojoule. This is what we're using, the unit for the heat. Okay, yeah. The next unit, that's going to be the temperature, the unit of the temperature. I probably didn't talk about in the first unit, and we're going to talk about the unit of temperature here. So there are several units we're going to touch with. We're not talking about the Fahrenheit, because this one is only used in US. Okay, we're using Celsius and Kelvin. Okay, Celsius is commonly used, but a lot of cases, not a lot of it, for every cases, we're going to using Kelvin instead of Celsius. So if you're talking about the conversion, let me just draw 3 lines. Then you probably will know it. So this one is Fahrenheit, Celsius, and Kelvin over here. Okay. So let's first see the Celsius, 0 Celsius. That's the freezing point of water, right? And 100 Celsius, that's the boiling point of the water. Okay. And our body temperature is about over here. That is about 36.8 Celsius. Okay, the people says 37. 37 probably fine. Okay. How about Fahrenheit? The 0, the freezing point for the Fahrenheit, 32. Right, 32. 32, there's a Fahrenheit. How about the boiling point? 212. That's the boiling point for the water. Body temperature, 98.6. Yeah. So that is the Fahrenheit. Okay. If you're talking about the Kelvin, Kelvin is the unit for absolute heat. Okay. Yeah. So for the Kelvin, the freezing point of this is 273. Okay, actually it's a 273.15, but you just remember 273. Okay, this is a magical number. 273 Kelvin, that's a freezing point. Then for the Celsius, for the boiling point, that's a 373 Kelvin. For the body temperature, then it's just 273 plus 36.8. That's it. Okay, so you can see that's going to be 300 40, wait, 09.8. Okay, so that is the Kelvin. So the difference between those is Kelvin, they do have absolute zero. The absolute zero is the zero. This is ideal temperature. I mean, nobody reached to the temperature yet. Okay, but this is ideal. So the technically people think about at absolute zero, this temperature, anything is frozen, including the molecules itself. So we talk about a molecule gonna have a kinetic energy, they're moving around, right? But at that time, at a 0 Celsius, a 0 Kelvin, no things can move, including the molecules itself. Okay, everything is frozen. So that is why we give it called absolute zero. Okay, absolute zero. But if you're talking about the Celsius, then that's going to be negative 273 Celsius. It's really low. And if you're convert to the Fahrenheit, it's probably is a negative 460. Okay, it's really, really, really cold. Okay, really, really, really cold. Okay, yeah. So this is what we talk about the change. And if you want to convert from Kelvin to the from Celsius to the Kelvin, Kelvin is just the Celsius, the number plus 273. That's it. Okay. Yeah. So the number of the Celsius, you know, you plus 273, then you got a Kelvin. And for the Kelvin to the Celsius, then that's just a Kelvin number subtract 273. Then that's it. Okay. Yeah. So if we talk about 298 Kelvin to the Celsius, then that's just the 298 subtract 273. Then this gives you 25 Celsius. So 25 Celsius room temperature. Okay, that is just a 298 Kelvin. Okay, so that is the unit change between Kelvin and Celsius. And then the last concept we're going to talk about is called the specific heat capacity. The people also call this as a specific heat. Or some of the sign, they just write SP heat. Generally, they are talking about the same thing. Or even the people write a QSP. This is also as a specific heat. Okay. So, oh, sorry, not the QSP. I'm doing wrong. Okay. So they're just writing the specific heat. There's specific heat, the symbol of the specific heat. Okay. Okay. This is a capital C. Okay. I know some of students, after we learn this topic, they have no idea what is the symbol for the specific heat. Okay. Specific heat is a capital C. Okay. Specific heat is a capital C. So what is the definition for the specific heat? The definition is just the amount of the heat is required to raise 1 gram of an object by 1 Celsius or 1 Kelvin. Okay, 1 Celsius, the change of 1 Celsius and 1 Kelvin, generally it talk about the same thing. Okay, yeah. So this is the specific heat. Again, specific heat is also how much heat, but this how much heat is used to raise 1 Celsius of the object by 1 gram of this object. Okay, so this specific heat is what we talk about is a intensive property, which means that this property will not change by the changing amount. You remember intensive, extensive property, right? Just like this property is just like a density. They never going to change. If you have a certain material, then this property will always the same. Okay, yeah. So specific heat. Some of the specific heat, I can make a. Let's just find out online what is the specific heat for the materials. Okay, so here we have the specific heat for those materials. Okay, yeah. So you see the specific heat are different. Okay, those materials, some of the material has really high specific heat, some of materials has a pretty low specific heat. You see that, right? So those are the specific heat. So what is the meaning of those specific heat? This is talking about how many of those kilo. The unit, if you see, that's a joule per kilogram or per K per gram, which means if I raise up 1 Celsius of 1 gram of lead, I just need a 0.128 joule of the energy. Okay, but if I want to raise up 1 gram by 1 Celsius of magnesium, I need a 1.024 joule of energy. Okay, so this is talking about how much the energy they need to absorb to raise 1 Celsius. Okay, to raise 1 Celsius. Then you can think about for the lead and the mercury, lead and the magnesium, which one will, if I give the same amount of heat, for example, if I give them 1,000 joule of the heat to heat up both lead and the magnesium, which one will raise higher temperature? Lead, for sure, right? Because lead, raise 1 Celsius, the lead just need a 0.128. So the amount of the heat can raise much higher compared to the magnesium, right? It's about like a 10 times difference. So this is what the meaning for the specific heat. Okay. Okay. So in this material, so what do you think? Which one gonna be the best material for cooking well? Think about cooking well. What is the purpose of the cooking well? You want to cook well. Once you turn on the stove, you want the materials the temperature of those materials go as higher temperature as possible, as faster as possible. That makes sense, right? Yeah. So what kind of material that's gonna be best? Lead gonna be the best, but are you going to use it for the cook well? Of course not. And then the best choice probably is gold. Wow. Do you have the money to buy a gold cook well? Probably not, right? Yeah. So maybe silver is also very expensive. So that's why a lot of people using copper as a cook well. Okay, but well, copper has some I mean, they can heat up the material very fast, but copper has another reason. I mean, it's expensive, but also is easy to be banned or be destroyed. So a lot of materials, they combine copper and other materials together. So that's why most of the case people using steel or iron as the cookware, because this guy still has a pretty relatively low the heat capacity, specific heat capacity, right? Yeah, but they're very, very cheap. Okay, very, very cheap, because we have a lot of iron in the Earth's crust. So this is what happens for those materials. If we have a lower specific heat, then this material gonna raise up the temperature really fast. Okay, if you're higher specific heat, then this guy will raise the temperature relatively lower, right? And then, do you know for the water, what is specific heat for the water? For the water, the specific heat is 4.184. That's a joule per K per gram. Compared to the magnesium, this guy is even higher. It's 4 times higher. So what is that meaning for the higher, the specific heat? We talk about when this guy raised 1 Celsius for 1 gram of the water need 4.184 joules. That means they need quite a lot of heat to raise 1. Okay, so that is why the people would like to go to the swimming pool or near the ocean or near the lake in the summer, because the water is still cool compared to the other materials. If you're sitting on the rock, that's going to be really, really hot. But if you go to the water, the temperature is still lower than your body temperature, because even they're having the same sunshine. Okay, they are absorbing the same energy from the sun, but they has really high specific heat. So the temperature they raise is relatively really, really low. So they still, you feel cold because you're kind of like releasing your heat to the water. Yes.
Does salt water have a different?
Yes, salt water they do. Okay, salt water, I'm not sure what is the difference, but the salt water, they do have a different heat capacity. Okay, so the solution is different from the pure water. Okay, yeah. I'm not sure, is it getting even colder? Maybe. Did you go to the salt or the ocean?
Yeah, I've been.
You've been in the ocean, right? Yeah. So the salt water they do has a little bit different, probably, but don't change too much. That really depends on the concentration of the salt in that. Okay. So that is why the people would like to we can use the water, a lot of water for the heat exchange. Okay, and there are some other materials that has even higher the specific heat, like a freon. Okay, so that's why the people using freon as a heat exchanger in the air conditioner, because when they absorb quite a lot of heat of the freon, they're still going to have a relatively lower temperature, so they can absorb quite a lot of heat and release that to the surroundings. Okay, yeah. So, okay, then how can we use this concept for some of the questions? There's a equation that's related to here. This is called Q equal to C time M time final temperature subtract the initial temperature. Okay, so C time M time final temperature minus initial temperature, and this is a delta T, and just a C time M time delta T. So the Q we already talked about. This is a heat. heat is equal to the C is a specific heat. M, this is a mass of the object. Specific heat time mass time change of the temperature. And this gonna be equal to the heat. Okay, so that means how much heat do we need? We just need to look at the heat. That's it. Okay, yeah. If you know the specific heat of the material, and you know what's the mass of this material, and you can measure what is the change of the temperature, you know how much heat this object gain or this object lose, right? We talk about the heat is used to change the temperature. So here, this is the how much heat it can transfer from one object, one temperature to the other temperature. Okay, so this is what we talk about: specific heat, time mass, time change of the temperature, and that's going to be equal to the heat. Okay, so I'm going to stop here. Looks like everyone is tired. I'm going to stop here, and then I will give you the study guide. Next class, we're going to continue to talk about the specific heat and how to use the specific heat in the next class. Okay, yeah. So let's take a break. And then I'm not sure, probably they're still working something over there. Okay, so you're going to stay here until the lab is available. Hey guys, we can go to the lab. The lab door is open.